Let's talk electrolytes. If you are in an in-person or if you're in a class with me where we did a lab on conductivity, we did talk about this during that lab, but we're going to go back over it again right now. All right. So when we look at electrolytes, we're looking at a solution that will conduct electricity. And the biggest thing that we need to understand about a solution that is an electrolyte is it's a solution that has mobile charge. So it will be a solution that has dissolved ions in it. Okay? So if I have an electrolyte solution, we've got dissolved ions. Those dissolved ions move around. We can conduct electricity. If I have a non-electrolyte, I do not have ions. And so I don't have mobile charge, so I will not conduct electricity. So my electrolyte solution lights the light bulb. My non-electrolyte solution does not light the light bulb. Okay, so we can define these. So our solutions that are made from substances that like sodium chloride, potassium bromide, soluble ionic substances. Okay? We did that dissociation to produce ions, or acids. We get dissociation there too. Okay? Non-electrolyte, so things like our table sugar, our sucrose, those are not going to conduct electricity. Sure, they dissolve, they do get solvated, and they can go into solution, but as they get solvated as individual molecules, not as ions, and so we don't have anything to conduct electricity. As we are dissolving, we replace our solvent-solvent interactions and our solute-solute interactions with those solvent-solute interactions, which hopefully that is familiar to you from your prep class when you learned about things like intermolecular forces. You should have learned some of this stuff as well. Water is a really, really good solvent because water is small and highly polar. Okay, so here's an electron density map of water with its partial positive and partial negative ends. And so we get that polarity because we have those partial positives. And so this partial negative end, okay, will attract cations. This partial positive end will attract anions. And so when we have a solvent that is soluble, or a solute that is soluble, such as sodium chloride, we get this sort of situation happening. So again, that partial negative end on water is going to interact with the positive cation. The partial positive end on water is going to interact with the negative anion. And so we get these solvent-solute interactions between those parts. Okay, and then we can look at the big picture. So again, we have our solvent-solvent interactions, we have our solute-solute interactions, and then we have to have a situation where now we can have our solvent-solute interactions occur. Okay. Now, as we are dissolving things, it's a very dynamic process. It's not static. Everything in solution is constantly moving around. And so if we have a solution that is saturated, and so we have excess solute floating around, as the solvent, in this case it's water, comes in, a new ion will pop off and then another one will crystallize back out, and it's a whole dynamic process where everything is constantly moving. Okay, we get these, we call them spheres of hydration. We say that they are hydrated. The waters will surround them because remember, water is polar. So it's just partial positive and partial negative. And so in order to fully interact with either that cation or that anion, multiple waters will surround the cation or the anion. Okay? Something like sugar, we still can get this to dissolve. So sugar does have a polar head on it, and it has a region that can participate in hydrogen bonding. So we know that water, one of the reasons why water has such unique properties is all of the hydrogen bonding that water does. And so in order to get something to interact, we need to have similar intermolecular forces. And so we get the ion dipole thing going on with water and an ionic substance. We can get either a dipole-dipole interaction or a hydrogen bond situation occurring where water will solvate with something like our table sugar. We still get those spheres of hydration. So we're still going to surround that based on where either we get the polar interactions or the hydrogen bonding interactions. When ionic substances dissolve, we call that dissociation. So if I have something like sodium chloride, it's solid, and I dissolve it in water, it will dissociate into sodium ions and chloride ions. Okay, so that's our dissociation. All right, if I have something like sodium sulfate, if it dissociates, we would get 2 sodium ions and a sulfate ion. Okay, and so that's our dissociation. Now, we can get 2 different kinds of electrolytes. We can get a strong electrolyte and we can get a weak electrolyte. So our strong electrolyte, we have complete dissociation. Okay, so something like sodium chloride. So these are going to be ionic substances that are soluble and strong acids and bases. Okay, so ionic substances that are soluble and strong acids and bases will be a strong electrolyte. So we get a nice bright lighting of our light bulb. A weak electrolyte, though, if you look here, I have hydrofluoric acid. And if you look at the molecular picture, I only have a little bit of hydrogen ion and a little bit of fluoride ion. Mostly, I have fully intact hydrofluoric acid molecules. And so a weak electrolyte is only going to partially dissociate. Okay? Okay, partial dissociation. And these are largely going to be our weak acids and bases. Okay, because they only partially dissociate. In solution, the major species of a weak electrolyte is the intact, undissociated molecule. The minor species are going to be your dissociated ions. Okay. Here's another example. So here I have hydrochloric acid and acetic acid. So looking at these 2 pictures, which one is the stronger electrolyte, the hydrochloric acid or the acetic acid? Well, if you look at the molecular pictures, the hydrochloric acid, which is a strong acid, dissociated completely, whereas the acetic acid, which is a weak acid, only did a partial dissociation. And so there's only a few ions in solution for the acetic acid. So this would be the stronger electrolyte. Okay, that's our stronger electrolyte. Whereas if we look at something like sucrose, well, it's a non-electrolyte. There are no ions in solution. No ions in solution. No mobile charge. Therefore, it's not an electrolyte. So we don't get the light bulb lighting up. All right, now if I were to take an ionic substance and try to light my light bulb while it was in its solid state, it's also not going to light up because, again, no mobile charge. But if I dissolve it in water, there we go, my light bulb will light up. Now, one caveat of that, though, is if I were to take this ionic substance that was a solid and I were to melt it, would it conduct? Okay, so think about solid versus liquid versus, other states. Okay, solid versus liquid is what we're looking at here. Something is liquid, is it all tied together or is it starting to move around? It's moving around. And so would it conduct? Yes. Okay, So if you make it molten, it will conduct. And then just as an example, again, strong electrolytes are going to be our strong acids and bases and our, fully soluble ionic substances. And so here, if you don't remember your strong acids and bases, here they are. You do need to know these. Okay, because if it's not a strong acid or base, it's a weak acid or base. And there's only a few strong acids and bases, and so it's very important that you're able to recognize those on site. Hopefully your prep class had you memorize these, but if not, you do need to know them going forward, because I will expect that you can recognize a strong versus a weak acid. And so you can see here some strong electrolytes, most soluble salts, strong acids, strong bases, weak electrolytes. Obviously, anything that's a weak acid or a weak base can fall under that banner of weak electrolyte. I just have a few defined here that are some of the more common ones that you might see, but if it's a weak acid, it will be a weak electrolyte. Okay? So, electrolytes. Know your strong acids and bases. It'll help.